Welcome. In this example, we're going to use Green's theorem. We're going to find the counterclockwise circulation as well as the outward flux for the vector field F given by, we have an M component, x cubed y squared I, plus an N component, 1/2 x to the fourth y times j. And the curve or the path that we're traveling along is going to be along two curves. We've got y equals x, and then along the path y equals x squared minus x. So we have two formulas that we use, one for counterclockwise circulation and one for flux. I've written each of those two formulas from Green's theorem here. So we're going to do a double integral over the region bounded by these two curves. And for circulation, we take n partial with respect to x minus m partial with respect to y. Whereas for flux, it's m partial with respect to x plus n partial with respect to y. So in order to work these problems, we need to state what m is, x cubed, y squared, as well as n, which is 1/2 x to the fourth y. So m, the partial with respect to x, will be 3x squared y squared, and m, partial with respect to y, will be 2x cubed y. Similarly for n partial with respect to x is going to be 2x cubed y. And lastly, n partial with respect to y is going to be 1/2 x to the fourth. Let's set up the integral for circulation. So my counterclockwise circulation, that's going to be the double integral over the region R of n sub x, which is 2x cubed y, minus m sub y, also 2x cubed y. And we'll integrate with respect to x and y depending on how our bounds work out. Well, one thing you should notice here is that my integrand simplifies to 0. Treating that as a constant, we have 0 times the area of that region, and 0 times anything is 0. So my circulation is equal to 0, which means that whatever our vector field is circulating, whether it be gas or water or electricity, there is 0 circulation. Okay, let's set up our flux integral. Here we have that flux is that double integral over the region R of m sub x, which is 3x squared y squared, minus n sub y, 1/2 x to the fourth dA. Now this integral is not going to simplify to 0. We need to come back up to our diagram to determine what my x and y bounds will be. Now, I do not want to integrate with respect to x first, because then I would have two different integrals. You'll notice my left and right are different below the y-axis as opposed to above the x-axis. So we're going to integrate with respect to y first, and that's convenient as both of my equations are in terms of y equals x. So I'm going to have x be my upper bound, and x squared minus x will be my lower bound. And then my x bounds will be going from 0 to 2. All right, so let's set this up. It's going to be the integral, as we just said, x equals 0 to x equals 2. And then the integral for y equals x and y equals x squared minus x. My integrand is 3x squared y squared minus 1/2 x to the fourth. And that would be dy dx. At this point, this should be a very easy integral for us to calculate. We would just be using our power rule to differentiate with respect to y first, plug in my y values, simplify, which is albeit a little bit messy and annoying, but we can handle it. And then we'll integrate with respect to x and plug in 2 and 0. The answer is 64/9. I encourage you to pause, give yourself a chance, make sure you can work this out as well. I'm going to pause and work it out myself and just have the answer here for us. So integrating each term with respect to y, that gives me a 1/3 y cubed here. The 3 and the 1/3 cancel. So I just have x squared y cubed. And then over here I have 1/2 x to the fourth, and I add a y. So this is the annoying part because we've got to plug in x for both of these y's. We get an expression minus plug in this expression for both of my y values, which looks like this. So we get into a little messy or busy algebra here because we've got to cube a binomial, but it simplifies down to something which looks like this. 3x to the fifth minus 7/2 x to the sixth plus 3x to the seventh minus x to the eighth. And of course, this is very easy for us to integrate using our power rule. And the power rule gives me 1/2 x to the sixth minus 7/14 or 1/2 x to the seventh plus 3/8 x to the eighth minus 1/9 x to the ninth. Plugging in 2 will give me 64/9 minus plugging in 0 gives me 0. So the answer for my flux is 64/9. And of course, if this was an application problem, we may be able to apply units to it, but that's something you would talk about in your physics classes. So I hope that helps you understand how to use Green's theorem. The main thing we wanted to feel comfortable here with would be setting up those integrals, because at that point, once we have them set up, the evaluation is generally pretty simple, but of course we ended up having to cube a binomial, which kind of made that messy, but completely doable from an algebra perspective. As always, email me if you have any comments, questions, or concerns.